Hi and welcome to the replacement lecture for the Software Engineering Methods Lecture 8. We are doing this lecture today as an online lecture because I'm actually going to be in Helsinki tomorrow, so I cannot give you the lecture. Since I'm also away next week, I decided that we will be doing this part 8 software architecture as an online lecture to give you some ideas first of all on what to do on the project 2 and to not miss 2 consecutive lecture events. So as you may have seen, we have now the Project 2, which is revealed. The Project 2 includes doing a systems architecture and use case plan for a media distribution system. The idea is that with your group, the same group you did the Project 1, the smokestack payroll system, you are to design a software architecture in 5 parts, which all parts supplementing each other, for Media Fun Corporation who wants to extend their business towards digital distribution of media. The project is in Noppa pages and it has set deadline for 16th of December. After the last part of the work is released, you still have 3 weeks to finalize your design, but I highly recommend that you start doing weekly contributions every time the new part is released. Then at least do some initial drafting work. The idea is that your project design, your architecture design, is graded based on thoroughness, the amount of details, how well or how sensible design decisions you have made, and how many internal conflicts there are. So keep in mind that if you want to design something, for example in part 3, it has to be similar or same design than in parts 2 and part 1, and also follow the same initial ideas you used in earlier parts in the latter parts. Anyway, the Project 2 instructions are online, so go to the Noppa pages and the Project 2 subpage, read that page and start to do your work. Okay, so this lecture I'm giving you online is probably going to be a bit faster than normally one given in lecture hall, but anyway, we will cover the entire topic of software architecture. Last time we had lectures 2 weeks ago, we were talking about making use cases out of requirements and what use cases describe. The meaning that when we collect requirements from customers, what sort of things we have to do to get the big picture out of the customers, so that we can then make actually something that can be implemented. Now then, based on these requirements, how to identify actors, how to make use cases, and finally, what sort of things we have to include in the use case description. We had a few examples of different detailed use cases, similar use cases or similar details that you are tasked to create in Project 2. So at the last slides of the lecture 2 weeks ago. Anyway, considering the one thing I have to emphasize on how these use cases are designed is the happy path concept. The happy path is the normal or default flow of events, meaning that this event chain is actually the one you should be following when you design, for example, how customer identifies themselves or signs into the system, and all the other alternative flows of events describe how different errors happen if we don't have connection to server, or if we don't have correct password, or the customer has expired account, or things like that. So on your design of use cases, always design it so that you actually expect that we achieve the actual thing we want to do, and later add alternative flows for situations where things don't happen like we wanted to. So basically, on the use cases, we can define use cases basically for every activity, but we also have to think what are the essential or priority use cases. This means that the cases which are architecturally important or have really important activities which we have to do first are usually the priority cases. Use cases we want to do to ensure the basic functionalities, like with the payroll system, connection to the bank, or in basically any web service, way to identify the user. So we want to have these details set, not only because the priority cases, they ensure that at least the basic functionalities exist. They also usually are related to things like the capabilities of hardware platform, or the requirements for internet connection bandwidth. So basically, if we have to do changes to these things later, it tends to be really expensive stuff. So not only are we defining use cases to actually make sort of a manual on how the system functions, we are also making use cases to collect the important parts, so that later we can actually ensure that the system probably gets done. And of course, overall, what we want to do is define the borders of the system. Define what sort of different systems, subsystems, databases, connection to banks, insurance companies, other information management systems, stuff like that exist, but also get the idea of what modules we are required to create for the software, what sort of things we have to consider. For example, if we have to manipulate gas pump at the gas station, in our case, if we are building an information system which handles buying gas from the gas station, we also have a list of different systems or borders or communication points, and then we can get the interface solved out, and we can actually acquire the information we need to create our own software. This is actually what means that they define who and what are interfacing the system and what is expected. So basically get the baseline on what sort of communication and with what sort of protocols or interfaces we have to work with. Also definition of other parts like the actors or the subsystems, or what sort of databases we need. A glossary of terms, meaning that we have set terms for different things, and probably we can manage our knowledge more easily, to get all the stakeholders involved and not to make any mistakes simply because two groups of people don't know what they are doing. So basically, identify the actors, get their roles, identify use cases, collect a list of priority cases, so we can get the important or critical information and start doing our software. So naturally, this leads to the software architecture. We have been talking about the analysis and collection of requirements for a while, so of course naturally now it's time to actually design something. So what is an architecture? It's a fairly common word. Architect is person designing buildings, and architecture is a collection of blueprints and stuff like that, which enables us to create buildings. But what actually is architecture in software? We don't have physical things, we don't have physical walls, or we don't have floors or elevator shafts or anything like that. So what actually are we designing when we are defining software architecture? And moreover, when we have something, what uses do we have for this architecture, since we are designing how the software should function, what sort of things the software should do, and or how it should be implemented. But who uses architecture, and what happens when we want to create software architecture? Well, there's another definition of architecture by Merriam-Webster dictionary, which defines the most common ways the people understand architecture. Well, of course, it's the art or science of building. That's the most traditional way to understand what architecture is. There's also formation or construction as the result of conscious act, creating something, creating a architecture, or using architecture to create something. But also, interestingly, this definition also recognizes the software industry. There's the fifth definition, the manner in which the components of a computer or computer system are organized and integrated. It's basically the definition we are looking here. It means that the architecture is actually roadmap or portrait of the software we are creating. Of course, it's a metaphor, in a sense that it's not actually something physical or something that exists in a physical sense, but it's more of a definition of different abstract parts like modules or components, software components, putting them together and combining them into a roadmap of combining them to do something even larger. Of course, we don't have one software architecture. If we consider all these different architectures which we may have in software industry, hardware architecture, network architecture, application architecture, system, software, different views into the system, it may just define the architecture in one workstation. For example, combining the network layers and the operating system and the application in in the software architecture, or just mapping the different modules and components into each other, giving them relationships like in application architecture, or just mapping where the different physical things are deployed, or where servers exist, what sort of connection we have between server and database solutions, sort of a hardware architecture, or simply how different nodes of are connected, for example, in cloud service, or are we using computation clusters, or do we have a central database where we store everything? Basically defining the network architecture. Basically different views into the software product. This is actually somewhat similar as in buildings. We don't have one architecture plan covering everything. We may have views into like the virtualization of what the building looks like when it's finished, or where the sewering plan or electricity plan or things like that. Different information about the same final design, and that's basically also what these different architectures are. They are defining what we are building from the viewpoint of hardware, from the viewpoint of networks, from the viewpoint of applications, and from the viewpoint of system. But overall, the software architecture is important to give an understanding of what we are actually doing to software developers. Like I said earlier, the software crisis was a situation where software programs became so large and complicated that one programmer couldn't understand the entire system anymore, or couldn't create software that was actually using the hardware solutions efficiently. So all these software designs and things like that are meant to make the design and teamwork and exchanging information easier. This is important since there's increase in distribution. We have more people, more systems we have to use. There's also increase in integration. We have different information systems connected to each other. For example, in companies, we have a production plant. We have a sales management system which is connected to bank, which is connected to possibly some customer service, SAP, SAP systems, which basically all mean that we end up with system that's definitely large enough that we simply cannot solve everything by just doing some thinking or drafting some small things into one blank A4 paper, but we have to create architecture for software so that we can actually know where these different interfaces are, and we also are able to document and define how these different systems can communicate with each other, what sort of services they offer, how they can exchange data from one system to another. Of course, this is not only the amount of integration within one company or within one information system. There's also problems because we have different operating systems, we have different platforms. We want to have a system which is able to function in PC, Windows system, Linux, smartphones, Apple, iPhone, for example, Android system or Microsoft phone. So overall, we have several different hardware platforms which are using several different operating systems which offer several different services, and we have many things we have to take into account, and that's the reason why we need architecture. We have to have something so we can exchange these or connect two systems to each other and exchange information. There's a list of different solutions which offer this object models or object infrastructure which are meant to make things easier, for example with platform independence, or making it possible to use different programming languages to create objects that are interchangeable. This is important if we consider older systems. We may have programming languages like Prolog or COBOL, which are no longer used to large degree. But still we have systems which use these languages, and they can only use or accept messages which are compliant with the restrictions of those languages or modules created by those languages. So basically it means that we can actually have something like a Common Object Request Broker, CORBA, which makes it possible to use several different old and new languages together in one system, so that we may have a server-side solution or bank-side solution which uses Java or COBOL or C++, and then we can make client or customer-side solution which is done with Python. And these two things can actually exchange information. It also helps us to integrate two systems together. If they follow these rules or are somehow compliant with these ideas, then it's more likely that we can actually come up with some sort of software that can software solution that can connect, for example, really old and really new stuff together. Similarly, there's also .NET infrastructure, where we actually have the possibility to use different programming languages to basically create one solution for object. You can see that we can basically use C#, Visual Basic or Java Sharp code. Also nowadays extended languages like Ruby and Python, where we just not compile them into the computer used form, but actually run them through this common intermediate language translation, which then creates runtime code. This is really important step between creating compiled code and some source code, because it means that we can use any programming language we are accustomed to define this part here, and it doesn't actually matter if you are proficient with Python or C# or Java. You always can create modules which can be used in this common language projects. It also, not only does it allow more freedom to use languages which are based on the personal experience or preference or usability aspects. If you need really optimized code, you can create a C module or C++ module. If you want to just manipulate things like strings or do some heavy string manipulation or database manipulation, you probably want something more dynamic, more adaptable language. So you can use something like Python and then compile both these things through the defined common language architecture and end up with two modules which are able to exchange messages or function as parts of a same system. So basically these two things are actually things that are made possible because we have software architecture, and these of course are more or less related to application architecture or software and network architecture, where we can combine different sorts of hardware platforms simply because they all use the same data transfer protocols, or at least understand the same protocols to exchange information. And then we can talk about building applications which come from several different backgrounds of things. Okay, so going into the short view on how these systems have been born. Of course, the history of architecture in computing starts from the first programs or first systems which were actually more than just advanced calculators for physicians or mathematicians. In the 70s we talk about programming in the large and programming in the small, meaning basically that we were just doing system-focused programming work. We were creating things for really well-defined or strictly defined architecture, and the idea that the code should be transferable was something that was always custom built into the system. Now, it's easy to understand this idea by looking into the, for example, things like video games or home PC systems. Basically, on the 70s, basically on every country there was their own solution on what sort of computer the people were using. There were Ataris, Sinclairs, the Soviet Union had their own solutions. And they obviously weren't meant to work together. But still, there were people who were tasked to create programs for them. And if we wanted to export something from one system to another, it was really, really large work. Okay, so during the 80s, we came up with the client-server architecture. So basically, the idea that you don't actually need to have two similar systems so that you can exchange information between two parts. We can make client-side solution on one platform like Windows system, and then create the server, for example, with Unix. That was actually really that was one really big distinction that held for a long time. You had different server-side operating systems and different client-side operating systems. For example, Microsoft operating systems still are more or less divided into client-side services and server-side services. Whereas, for example, Linux operating systems are the hybrid in their design architecture, in a sense that you basically can turn your desktop client into a server just by adding certain new parts, or you can use your server computer as a desktop if you really need to, because it's the same system, it just has the attributes and abilities of two different operating systems. This was also the era when the databases and data processing on separate places became more prominent. If we took the server to one place and put the clients on another place, then we also could have different databases which were connected via database management logistics, and we could do data processing on one place and collect and retrieve the data or store the data to another place. Going to 90s and to aughties or year 2000 and 10 years forward, the component architecture and the module architecture, object-oriented programming, started to mean that the system architecture or software architecture actually became even more detailed and went into the actual applications. Not only did we have different entities in different places like database, server and client, we also had internal components like user interface and network interface and input interface, and different components, modules you could use in several programs to exchange data. This also basically is what made internet possible. We have different sorts of systems which can exchange information over the same TCP/IP protocol, so internet was possible to create, to form. It wasn't actually created, even though Al Gore says something else. But since we had since we had protocols which allowed different systems to communicate with each other, we also had internet. We had mobile technologies, and the era of calling into these BBS data server boxes was actually ended by simply people being able to connect from one computer to another. Some computers were running hosting services for websites, others were just retrieving them for browsers, and we had the internet. And it didn't take long that when the internet was born, then the web services, web stores, search engines, other things started to appear, and meaning that not only did we have an internet where we can find different sorts of material more easily, but we also needed to have programming languages and architectures and different ways to implement new services on this new internet. Okay, so considering has this development been positive? Well, obviously we have more sophisticated systems. They are more capable, they have more computing power than ever. But if we consider the amount of different technologies required to say that you really understand what's going on in software industry, it's actually interesting that during the 80s there were really only few things. If you understand COBOL programming language, were familiar with Oracle databases and Unix operating system, were able to use IBM and knew something about C language, then you basically understood everything that there was to know about software industry. Now we have a huge amount of technologies compared to that. We have different operating systems, platforms, programming languages, different places or different service model. Are we doing web service, or are we doing client-side service? Are we doing cloud service? Different things, meaning that the complexity is actually increasing all the time. So the architecture which was created to actually make it easier for two systems to connect to each other or to define interchangeable parts is actually more needed now than it ever was, simply because we have more technologies, more different options, and more different things we have to take into account. Okay, this is the end of the first part of the lecture recording. I'll be seeing you back on the part 2.